In this module of the first chapter of Biodemography, Module 1.3, I will cover concepts and methods for exploring and summarizing demographic data. Visual inspection of raw data is the first step to understanding numerical information collected in demographic studies. Engaging with the numbers at this early stage helps to identify patterns, ascertain nuances, spot anomalies, compare trends, anticipate statistical requirements, conceive mathematical models, and envision appropriate graphics. This early process of data analysis, even when data is still being collected, is often used to either redirect studies with what appears to might be a dead-end approach, or to fine-tune those in which the experimental results reveal new discoveries that need to be replicated or validated. As an example, consider the scatter plots of the lifetime reproductive data for 3 species of fruit flies. This is a broad pattern that shows the overall range of lifetime egg production is similar for the medfly and Drosophila, but nearly twofold greater in the Mexican fruit fly or Mex fly. With respect to infertility, there were very few Drosophila females that laid few or 0 eggs, but there were a relatively large number of medflies and the Mexican fruit flies that laid either no eggs or a minimum number. With respect to high reproduction, the drop-off in numbers of females laying large numbers of eggs was abrupt in the medfly, but more gradual in the Mex fly and Drosophila. The data shows that whereas in the Mex fly there was a relatively uniform distribution of individuals across the total range of lifetime egg production, the distribution was more concentrated in both the medfly and Drosophila, with drop-offs at both high and low values of lifetime egg production. Standard deviation. The standard deviation, acronym SD, is a measure that is used to quantify the amount of variation of a set of data values. It is computed as with the familiar formula, standard deviation equal the square root of the dividend of the sum of squares n minus 1. Several characteristics of the standard deviation merit comment. First, the number of standard deviations provides estimates of the values of data that lie within different percentages of the mean. Specifically, 1, 2, and 3 standard deviations provide statistical first approximation values of the data that lies within 68%, 95%, and 99% of the mean, respectively. Second, standard deviations are expressed in the same units as the data, unlike the variance. For example, 1,000 eggs plus or minus 200 eggs, standard deviation. Third, the standard deviation is commonly used to measure confidence in statistical conclusions, with a reported margin of error typically twice the standard deviation, i.e. half width of the 95% confidence interval. Because different data sets can yield the same standard deviation, a shortcoming of this statistic is that it sheds light on relative spread but little else. This is illustrated by considering the standard deviation for each of the data sets on lifetime reproduction in fruit flies. Although the larger value of standard deviation for the Mex fly shows that there is larger variation in the Mex fly relative to the other species reproduction, the similarity of standard deviations between the medfly and the Drosophila does not tell us anything about the details of why they are similar. In fact, as shown here, the distribution of lifetime egg-laying patterns between these 2 species is quite different. Histograms are, as shown in the last slide and to the left, are graphical representations of the distribution of numerical data and provide estimates of the probability distribution of continuous variables such as birth and death distributions. They differ from bar charts that are used as graphical tools for categorical data like gender, ethnicity, species, with the bars being separated spatially as in the previous figure for the average egg production data from different species. Histograms for egg laying provide more detailed information than previous depictions or summaries. For example, the histograms show a flatter and wider distribution of egg laying in the Mexican fruit fly relative to the other 2 species. The large number of females who laid 0 or few eggs in the Mex fly and the medfly is readily apparent. Box plots are graphical depictions of numerical data in quartiles, one form being the box and whisker, of which is shown here for the fruit fly reproductive data. These plots provide a summary of the data and its variation in 5 numbers, including the minimum and the maximum, and 3 quartiles, including Q1, 25%, Q2, 50%, and Q3, 75%. These metrics are used to compute range, that is max minus min, the interquartile range, acronym IQR, which equals Q3 minus Q1, the mid-hinge, which is the average of Q1 and Q3, and mid-range, which is the middle of the range. These are computed as interquartile range equal Q3 minus Q2, mid-hinge equal the sum of Q3 and Q2 divided by 2, and the mid-range equal the max plus the min divided by 2. The box plots of the fruit fly reproductive data reveal a number of important relationships and patterns. First, a quarter of all medfly females produce 300 eggs or fewer, and this first quartile is over half that for the other 2 species. An underlying reason for this low value is that a large fraction of medfly females are infertile, that is, 0 egg layers. The box plots also show that the third quartile of mexfly reproduction approaches the maximum of the other 2 species. In other words, the lifetime egg production of a quarter of all mexfly females is greater than the most fecund females in both the medfly and Drosophila. Additionally, the plots show that the Mexican fruit fly IQR of nearly 1,500 eggs per female is over 100% greater than that for Drosophila, which is around 700, and around 75% greater than the medfly, which is around 850. This ends Module 1.3 on data visualization and summarization.